Okay. In the last class, we have discussed assignment problem, and I have shown the answer also how to solve that problem using branch and bound technique. And we got a state space tree like this. Okay, this is the complete state space tree for the assignment problem. After solving the problem step by step, finally you write one complete state space tree which shows the solution to the given problem. Okay, so here let me to spend 1 minute on this solution. Since in the branch and bound technique, you have to calculate the lower bound or upper bound value depend on the given problem. The assignment problem, we need a lower bound value. So we have calculated the lower bound value, and in each level we have selected the best node having the bound value, best bound value, and that node will be explored. Okay, and this process is repeated until you reach the solution. So this is about the solving an assignment problem using branch and bound technique. So today I'm going to discuss about knapsack problem. You know already the problem statement of knapsack problem. So this problem statement already we have discussed in the brute force chapter only. Till now we have seen two solutions or two methods to solve this problem. One is the brute force technique and another one is dynamic programming technique. And in dynamic programming technique, one more variation is that using memory function also we have solved this problem. See, today we will see how this problem can be solved using branch and bound technique and how it is efficient compared to the previous techniques or previous methods. So try to tell the problem statement. N items are given and we know the weight and values of each item and knapsack capacity W is given. We have to find the most valuable set of items that fit in the knapsack. Means most valuable means whose profit is maximum and total weight should not exceed the knapsack capacity. So now two methods also. Okay, but in greedy technique, very first step what we need to do here is you arrange the instance given problem instance in descending order of their value to weight ratio. I will explain you later what is this value to weight ratio with an example. Okay, you have to for every item you have to calculate the value to its weight ratio. uh, Descending order of this ratio we have to arrange the first the items. Okay, so this is how the value to weight ratio is calculated. If V1 is the profit of first item or the value of the first item and W1 is the weight of the first item, calculate the ratio. And again for the second item also calculate the ratio. So on for the nth item also calculate the ratio. So arrange these all the items in the descending order of their value to weight ratio. So that in the list I should get the item whose value to weight ratio is maximum as the first item. Okay. So this is called as then we are going to pick the very first item which gives the best payoff per weight unit. Okay, best payoff per weight unit. That's what the maximum value to weight ratio. So that item is going to be selected first. If it is not violating any problem constraint, then that item is going to be placed in the knapsack. You know the constraints already. The constraint is one is the max total weight should not exceed the knapsack capacity, and always we want to give the maximum or the optimal solution. That is the maximum
Hello,
profit
sir. Excuse me, sir.
using branch and bound technique. Yeah, yeah.
Sir, we
Yes,
can't.
Rudra Prasad.
We can't see the screen properly, sir. Zoom out little more, sir.
Okay, 1 minute. Now is it okay? Same?
Yes, sir. No, it's okay, sir.
It's okay. Okay, fine. Okay, if suppose if you face any problem in viewing this presentation, you can stop my presentation at any moment of time. Okay. Yeah. Now the idea is, it's a very simple idea. As I already told you, you have to calculate the bound value first. Since in this problem, the optimal value is a maximum value. Okay, it's not like the assignment problem. In the assignment problem, we want to solve the problem with less cost. So minimum value we have taken as the bound value. But here we want the maximum profit. You have to consider the upper bound value. That is the maximum value as the upper bound value. Upper bound value is the bound value here. Okay. So initially we have to calculate the bound value for the root node. I will explain you how to calculate the bound value for the root node. And that value will be the upper bound. Means that is the maximum profit you may get at most, not beyond that, not more than that. So your optimal solution will be equal to the calculated upper bound value or lesser than that upper bound value. It will not go beyond that upper bound value. Branch and bound technique. So first, for the root node, upper bound is calculated. When I am considering the root node, no items are placed in the knapsack. At that time, whatever will be the upper bound, that value will be calculated. Next, by placing one item into the knapsack, one by one item into the knapsack, in the knapsack, so we are going to change the upper bound value. Okay. Finally, when the knapsack is full, when all the items are considered for the insertion, then we will we will end the process. We will end this process with the optimal solution. The final bound value will be the optimal solution to the given problem. Okay. So now, so this is the formula to calculate the upper bound value. Let me explain this formula in detail. U is the upper bound value is equals to V plus small v. V plus means the value which is gained till now, means the value which is gained in the previous steps. Okay. The value means profit gained till now plus big W minus small w. What is the big W? Capacity of the knapsack, maximum capacity of the knapsack, minus small w means the total weight of the items which are placed in the knapsack till now. So how many items you place in the knapsack? Big W minus small w will give you the remaining capacity. For example, if the knapsack capacity is 6 and I have placed 2 items in the W minus W, that is 3. 3 will be the remaining capacity. Okay. So that remaining capacity is multiplied with profit weight ratio of the next item. If you are doing for, if you are calculating the upper one for the ith item, then you have to multiply it with the profit weight ratio of the I plus one item. Okay. I plus one item. So that value, the value of this formula will be the upper bound value. So I am going to use this formula in solving the problem. Then clearly you can understand. Okay. So I have explained all these terms. Okay. Let me to repeat again. UB means upper bound value. Small v is the profit gained till now. And big W is the maximum capacity of the knapsack. Small w is the total weight of the items which are placed in the knapsack. So W minus W is the remaining capacity multiplied with profit weight ratio of the next item, that is I plus 1, next item. So before using this formula, you have to arrange the items in the descending order of their profit weight ratio. Don't forget that step. That is very important. Okay, we have to arrange the items in the descending order of their profit and weight ratio. Okay. Now this is the example given. We have to solve this problem using branch and bound technique. The very first table what you're observing, you will get a problem like this in your exam. Okay. First column will tell you the item number. Second column is the correspond weight of each item, and value. Third column is the value, profit of each item, and big W means capacity. So in this example, I have taken 10 as the maximum capacity of the knapsack. What is the first step? What I told you? First, you calculate the profit weight ratio of each item. Oh, see the second table now. In the second table, for every item, I have calculated the profit weight ratio. It is very simple. VI divided by WI. 42 divided by 7 is 6. 12 divided by 3 is 4. 40 divided by 4 is 10. And 25 divided by 5 is 5. Okay. This is the profit weight ratio calculation. After calculating the profit weight ratio, arrange the items in the descending order of their profit weight ratio. Okay, now observe here. In the given problem, third item ratio is 10 and the next best one is 6, means the first item, and the next best one is 5, fourth item, and the last one is 4, that is the second item. So you see the third table now. Here I have arranged all the items in the descending order of their profit weight ratio. 10, 6, 5, 4. 10 means third item. In bracket I have written the original number of that item, 3. So before that bracket, what we have written, this is the for serial number we have written 1, 2, 3, 4 like this. Okay. So these numbers I am using in solving the problem, but original number of that item is 3. And second item is first item of the given question. Third item is fourth item of the given question. Fourth item is second item of the given question. And these are the profit weight ratios. In the same way, you you consider its corresponding weight and value also. Okay, don't forget arranging this weight and value also here according to the profit weight ratio. Okay, so this is the very first step what you have to do in a given problem. The problem is given like this: calculate the profit weight ratio, arrange the items in descending order of their profit weight ratio. Okay, and this problem is called as 0 1 knapsack problem. The reason is 0 means item is not placed in the knapsack. 1 means item is completely placed in the knapsack. That is the meaning of 0 1. You know this problem statement already. We have taken 0 1 in dynamic programming also. Okay, we have represented the solution vector using zeros and 1. 0 means item is not placed. 1 means the item is completely placed in the knapsack. Okay, now I told you already, in branch and bound technique, the problem is solved used by constructing the state space tree. Okay, so here I'm going to construct the state space tree using this table. You use the recent table, don't use the original given table. Okay, use the recent table. Once you write the formula for upper bound calculation, upper bound calculation is done using the formula V plus W minus W into VI plus 1 divided by WI plus 1. You know the meaning of all these terms. Okay. So very first node we will calculate now. Very first node number is 0. For every node I have given the numbers here. You remember these numbers also, because in my presentation you can see the calculation also for every node. So first node is a root node. First you write one box like this and write 0 as the number of name of that node, and write WV as 0 0. W means weight of the weight till now, how much weight is placed in the knapsack? That is what W, small w, I told you already in the formula. Okay, and V means how much profit you you gained, okay, by placing an item. Okay, that is a V. Okay, and upper bound is calculated using the above formula. Okay, so for the first node, weight is 0 because no items are placed. V is profit gain, no profit is gained, so hence where profit is V is also 0. Now let me re-explain how upper bound is calculated for the first node. Okay, now see this formula. It's very simple. You just remember this formula, you will get a complete solution, correct solution to the given problem. So for node 0, upper bound is calculated like this. 0 means V. V means the profit gain till now is 0 plus W minus W. What I told you, big W means maximum capacity 10 minus small w means total weight placed till now. This is small w is 0. Okay, 10 minus 0 into, so Vi plus 1 divided by Wi plus 1 means the profit weight ratio of the item. Which item you are going to consider now? We are going to consider. Okay, zeroth node means no items consider. Now from zeroth node onwards, I am considering the item. So first item to be considered is the item whose profit weight ratio is 10. Okay, so hence it is multiplied by 10. So what is the value of this equation? 100. Now 100 will be the upper bound value. See, for the root node, how much you are getting the upper bound? No, that is the maximum. At most, you may get a profit 100, not beyond 100. Okay, always the optimal value is equal to 100 or less than 100 for this example. Okay, I hope it is clear. Now let me to move on to the next level. Now I am going to explore the root node. This root node can be explored by considering two choices. One is by placing the item 1 in the knapsack, or by without placing the item into the knapsack. So that is what W1. W1 means with item 1. WO1 means without item 1. Okay. W1 means with I am going to place the item 1 into the knapsack with one. Okay, and the next choice is without one. Suppose if you are not placing the first item into the knapsack, so what is the node? What is the child node? Okay, so I am in the next level, I am going to consider two child nodes, node 1 and node 2. Okay, first let me to write these labels. Node number is 1, and what is W, what is V now? So W is the weight. So now I am placing first item into the knapsack. What's the weight of first item? 4. Okay, 4. Weight equals to 4. What is the profit gain? 40. Now you see the recent table. Don't see the original table. See the recent table where the items are arranged in the descending order of their profit and weight ratio. W equals to 4 and V equals to 40. Okay, profit of the first item. Now for the node 1, again you have to calculate the upper bound. Upper bound UB is calculated using again the same formula. So now let me explain how node 1 values are calculated. It is already shown here. Node 1. Node 1 is upper bound equals to, okay, V, small v. How much here? 40 plus into remaining capacity is how much? Maximum capacity is 10 minus, you are placing first item, no, means weight is equals to 4. 10 minus 4 into, what is the profit weight ratio of the next item? Now I have placed the item 1. What is the next item now? Item 2. Item 2 profit weight ratio is how much? 6. Okay, multiply by 6. I hope this explanation is clear. Let me to repeat if it is not clear. Upper bound for the node 1 is equals to V. You see the node here, only V is there. We have written V equals to 40. 40 plus then remaining capacity 10 minus first item is placed, no, 4. 10 minus 4 into next best profit ratio. Next item's ratio is 6. So the value of this equation is equals to 76. Okay, so node 1 calculation is over, node 1 is generated completely. Now generate construct node 2. So node 2 is coming because of not placing the item 1, means without 1, without item 1. Okay, now what is w? W remains as 0 because its root value is also 0. Now it still remains as 0 because I am not placing the first item, and value remains as 0. Okay, 0 only. Now calculate the upper bound. So upper bound calculated using the again the same formula. Now here I am going to show how upper bound for the node 2 is calculated. So now what is small v here? Small v is 0 plus what is the remaining capacity? 10 minus 0, because 10 is the maximum capacity and 0 is the weight gain, weight placed till now, into, okay, next items profit ratio is how much? 6. So now solve this equation, you will get 60. Now 60 is the upper bound value of the second node. Okay, level 1 is finished now. Now next what I have to do? Now I have two child nodes here. In these two child nodes, which node is best? How to decide the node as the best node? See the upper bound value. First node 1 upper bound value is 76. Second node upper bound value is 60. Since in this problem, I want the maximum profit, so I go with the maximum value. So I am going to treat node 1 as the best node. Node 1 as the best node and whose value is equals to 76. Okay. Now I am going to ignore the node 2 because it is I am going to treat it as a non-promising node because its upper bound value is 60, which is lesser than 76. Okay, that node 2 path is terminated there itself. Now go with the node 1 and explore node 1. See, once I coming to node 1, one decision is finalized now. What is the decision? Item 1 is placed in the knapsack. Okay, now I have three more items left. Okay, I have to decide whether can I place second item, can I place third item, can I place fourth item. Now okay, this is also decided using the same method. Okay, now you explore the node 1 by considering the second item. Again, for second item, two choices. One is with second item, without second item. Okay, with second item will generate the left child, without second item will generate the right child. Okay, now let me explain how the node 3 is generated. So node 3 is generated because of placing the second item with item 2. Okay, what is the weight of item 2? 7. Okay, so weight of the second item is 7. Again, I'm repeating, see the recent table. Don't see the original table. Okay, in the recent, in the final table, the second item is first item of the original table. Okay, so second item weight is 7. Now, how much weight filled till now in the knapsack? 4, because I have placed the first item in the knapsack. So weight till now gained no, filled in the knapsack is 4. If I place the second item, what's the weight of the second item? 7. 4 plus 7, it becomes 11. Okay. Now observe the node 3. In node 3, I have written W as 11. Is 11 is less than the capacity of the knapsack? No. Capacity of the knapsack is how much? 10. So weight, total weight should not exceed the knapsack capacity. It violates the problem constraint. Hence, you terminate the node 3 there itself. Node 3 is not a promising node because it's violating the problem constraint. So for node 3, you no need to calculate the V value, you no need to calculate the upper bound value also, because in the beginning only it's violating the problem constraint. The total weight is becoming 11. 11 is greater than the maximum capacity of the knapsack. So my fifth two item decision is not suitable now. It is not a correct decision. So now let me to go with the another choice. Another choice is without second item. If I go without second item, then my what is my W and V value? W and V value remains as the node 1 value only. W is 4 only, V is 40 only. Just upper bound value is changed now. Okay, how upper bound value of the node 4 is calculated? Again using the same previous formula. Let me explain the calculation for upper bound calculation for the node 4. Okay, upper bound is equals to V. V is how much for the node 4? 40 plus remaining capacity is how much? Maximum capacity minus current weight. So 10 minus 4. Okay, into now which item you are for which item means I'm what will be the next item you are going to consider? That is the third item now, because this is the calculation we are doing for without 2. So what is the next choice? Next option, third item. So hence 10 minus 4 into 5. Okay, third item profit weight ratio is how much? 5. So 10 minus 4 into 5. So what is the value of this formula? It is 70. So 70 will be the upper bound value of the node 4. See, again I am repeating, node 4 is constructed for without 2. Means one is already considered, item 2 is also considered, but one is see, considering and placing is different. I'm considering the item for calculation, but item 1 is considered, yes it is also placed. Item 2 is considered but not placed. Okay, so when I am not placing item 2, I am constructing node 4. In node 4, I have what is the next my choice is item 3. Hence in the equation I have multiplied the value with the remaining capacity with the value 5. 5 is the profit weight ratio of the third item. Okay, now observe node 3 and node 4. Node 3 is already treated as a non-promising node, and what is node 4? It is 70. So that is the currently that is the best one. And you can even you can see the node 2 also. Node 2 profit is how much? What is the upper one? 60. Even if you compare with the node 2 also, node 4 is the better one. Okay, let me to explore node 4 now. Okay, I hope till now it is clear. Now I am going to explore node 4. Okay, so now I have considered two items, 1 and 2. Now I have to go with the item 3. That is shown in the next slide. Okay, now observe here. For your reference, again, I am showing the table and the formula. Node 3, which is a part of the previous slide, and node 4 is also explained in the previous slide. Now node 4 is explored now. Okay, to explore node 4, I am going to consider the third item. So with third item and without third item. Okay, if I go with third item, what will be the W value? Current W is 4 plus third item weight is how much? 5. 4 plus 5 is 9. See the fifth node, node 5, where I have written the node number as 5. W becomes 9. How it is 9? Previous W was 4 plus with 3 means with third item. Third item weight is 5. 4 plus 5 equals to 9. Now what is V now? Previous V was 40 and you are going with third item. Third item weight is value is 25. 40 plus 25 is equals to 65. So in the node 5 value is equals to 65. Calculate upper bound using the again same formula. Okay, so upper bound is equal to how it is calculated, shown here. You can observe node 5. See the node 5 upper bound is equals to 65 V, 65 plus 10 is the maximum capacity minus how much weight placed till now? 9. 10 minus 9. Okay, 10 minus 9 is the remaining capacity into what is the profit ratio of the next item? 4. Okay, that is the fourth item. 4. There is only one item left now. 4. What is the value of this equation? 69. So upper bound value is 69 now. Okay. If I go with without item 3, you will get the node 6. See, for every item you have to calculate with and without. Okay. So node 6 calculation. In node 6, it is coming because of without third item. So since it is without third item, W and V value remains same as the W and V value of the node 4. That is 4 and 40 only. Only upper bound changes now. What is the upper bound of the node 6? Okay, calculate. See the calculation. Node 6 calculation. 40 plus 10 is the maximum capacity minus weight is how much? 4 into profit weight ratio of the next item. Next item means fourth item. So what is the value of this equation? 64. You calculate it once again. Okay. So it is 64 now. Now in this level, I have two nodes, node 5 and node 6. Observe only these two nodes. Choose the best one. Yes, best one is node 5, whose upper bound value is 69. Okay, now I have to explore node 5 now, because still I have to consider one more item. Okay, so what is the last item? Item 4, with 4 and without 4. Again, you will get two child values. If I go with fourth item, what is the weight of the fourth item? 3. 3 plus, what is the weight placed till now in the knapsack in the fifth node? 9. You see the fifth node, how much weight is placed in the knapsack? 9. If you place fourth item also in the knapsack, then what is the total weight? Total weight becomes 9 plus weight of the fourth item is 3. 9 plus 3 is 12. So in this, observe the seventh node now, node 7, where the total weight becomes 12. 12 is greater than the maximum capacity of the knapsack, that is 10. So hence, node 7 is not a promising node. It's violating the problem constraint. Okay. Now I am going in the right side. In the right side, I will get another node, that is without item 4. I told you already, with whenever you are going in the label without, you just copy the W and V value of the its parent node. Okay. Without 4 means eighth node. Its parent is fifth node. Fifth node W and V is 9 and 65. Copy it as it is. Just calculate the upper bound value for the node 8. Again, using the same formula. Okay. Upper bound value for the eighth node is, okay, 65 plus 10 minus 10 minus 9. Okay, 10 is the maximum capacity, and I have placed on total weight placed in the knapsack is 9. 10 minus 9 into, what is the next item? All means already I'm doing this calculation for the fourth item, so all the items are covered, no, so no more items are left, hence profit weight ratio is equal to 0. Now what is the value of this equation is 65. Let me give the explanation again. 65 is the current profit plus remaining capacity is 10 minus 9 into profit weight ratio of the next item. Since we are considering fourth item, no more items are left, so take 0 as the profit weight ratio of the next item. Okay, next profit weight ratio is 0 because no more items are there. So value of this node 8 is 65. Now all the items are considered. Now you can see node 8 is the optimal solution. So what is the maximum profit gain is 65. The value what we have written in final upper bound, what value we got in the node 8, no, that is the optimal value. Okay, this is the optimal solution. Now in the next slide, I will show you the complete state space tree. All these parts are connected. Okay, complete state space tree along with the final answer. Okay, so now observe here. So this is the complete state space tree what we have constructed till now. Node 0, root node. Upper bound is 100 initially. No items are considered. No profit is gained. So hence W equals to 0, V equals to 0. Next level, node 1 and node 2 are calculated with item 1, without item 1. Again calculate the upper bound for both the nodes. Compare the upper bounds. Take the maximum one, 76. That is node 1. Explore the node 1 with 2 and without 2. You will get node 3 and node 4. Node 3 weight is becoming 11, violates the constraint. Stop that node 3 there itself. Node 4 upper bound is 70. Explore node 7, node 4 again. You will get with 3 and without 3, two nodes. Node 5 69, node 6 is 64. Okay, but when I compare upper bound, 69 is best. That is node 5 is best. Again explore node 5 by considering fourth item and without considering the fourth item, with 4 and without 4. Node 7 is with 4, weight becomes 12. 12 is bigger than 10, capacity of the knapsack. Terminate node 7. Node 8 is without 4 and no more items are left. Tree construction stops at node 8 only, and the value gained in node 8 is 65. That is the optimal solution. So optimal value is 65. Now we have to find out what are the items placed in the knapsack. Now it is very simple. In this tree, you just follow, you traverse this tree from root to solution. Root is what? Node 0. Solution is in node 8. You see the path. You just search the node 8 from node 0. How you can search node 8 from node 0? Start from 0. go towards left side, that is with 1, so means item 1 is placed. Next, if I go left side of 1, will you reach node 8? No. So I have to go the right side of node 1. Okay, that is in the, what is the label of right side of node 1? Without 2 means item 2 is not placed. Again, go left side of node 4 means with 3 means item 3 is placed in the knapsack. Shall I go in the left side of node 5? No, not you. If you go in the left side, you will not get the goal node. Goal node is node 8 now. So from node 5, I should go in the right side. What is the label of the right side? Without 4 means item 4 is not placed. Now I reach the node 8. It's very simple. Find the path from root to 8. Root to 8 is with 1, without 2, with 3, without 4. Okay, node 8 is reached. So two items are placed. That is item 1 and item 3 are placed. Item 2 and item 4 are not placed in the knapsack. So for your reference, I have given the recent table again. See the final answer what I have written. V, profit, optimal solution is 65. Total weight placed in the knapsack is 9. And the solution vector is 1 comma 3. 1 comma 3 according to the recent table. According to original table, item 1 means third item. Item 3 means fourth item. Means with respect to the given original question, original item 3 and original item 4 are placed in the knapsack. So this is what solving the knapsack problem using branch and bound technique. Okay. So I have given one more question here. So this is one more problem instance. I will upload this presentation in the Google Classroom. You copy this question and apply the same branch and bound technique concept what I have explained till now and solve this problem. Solve this following instance of the knapsack problem using the branch and bound technique. 4 items, corresponding weight and value is given, and maximum capacity of the knapsack is 16. Okay. Yes. Now let me to stop the presentation now. If you have any doubts, now you can ask. It is open for discussion now. Yes, my presentation is clear. If you have any doubts, you
Yes,
can
sir.
ask. Yes, any doubts in this in solving the knapsack problem using branch and bound technique? See, when I start, yeah, when I started this class, around 41, 42 students were joined to the class. Now, when I end the presentation, only 37 members are here. What is this, huh?
Sir, when you say we'll end up, they'll leave the classroom, sir. That's it.
No, they are very busy with some other work, I think. Huh? At least they can't wait for 5 or 10 more minutes, so that even others may have the doubts. Definitely, those clarification for those doubts will help others also. What is this? Huh? Yes, okay. Let it be. I see. Our efforts will become useful only when uh, you from your side also response is there. Then only it becomes very useful. So I'm going to stop.